Tonight, we're going to talk about a deadline that almost nobody hears, and about the strange, gentle arithmetic of a star that will not hold still. Picture, if you can, an Earth that is still recognizably Earth. The continents are where you left them, more or less. Drifted a little, but their outlines are the outlines you would still call by the old names. The Pacific Basin is a basin. The Atlantic is a long trough between two familiar coasts. Only the water is gone. The ocean floors lie exposed to a white sky, floored with salt in slow, glittering pans, and where the reefs used to be there are only ridges of pale carbonate, the calcium memory of animals that lived here for hundreds of millions of years and then, one by one, over a span too slow to see, went quiet. The land is empty, not in the way a desert is empty, but in the way a house is empty after everyone has moved out and taken even the curtains. There are no forests, there are no grasses. The great green machine that ran on carbon dioxide and sunlight has been switched off from the inside, and the rocks that outlive it are already beginning to record its absence layer by layer in bands of oxidized iron and buried salt. There is a sun in the sky, and it is a little larger and a little whiter and a great deal brighter than the one you know. It is still an ordinary star. It is not dying. It has done nothing dramatic. It has only continued patiently to do what stars do. This is not the end of the world in any Hollywood sense. There is no explosion, no red giant swallowing the planet, no darkening. The sun in this scene has something like 4 billion years of ordinary life still ahead of it. And that is precisely the strange thing we're going to sit with tonight, because when people talk about the future of the Earth, they almost always talk about the last of those years. They talk about the moment, 5 billion years from now, when the sun will swell into a red giant, when the inner planets will be reworked, when whatever is left of our world will be pulled apart by tides or engulfed by an atmosphere of stellar gas. And that story is true. It is one of the great long stories astronomy has ever told us. But it is not the story that matters most for anything alive. The story that matters most is a quieter one, and it happens far sooner. It is the story of what happens to a living planet while its star remains, by every stellar standard, perfectly stable. It is the story of the deadline nobody hears. The number to hold in your mind softly is 1 billion years, not 5. 1. Somewhere in that span, and probably closer to its far end than it is near, the Earth's oceans begin to leave the sky. Complex life, the kind that keeps books and builds nests and photosynthesizes in fields and swims in schools, runs out of the conditions it needs to continue. Different lines of research disagree by a few 100 million years about exactly how and exactly when and which piece fails first. Some models put the moist greenhouse threshold, the point at which water begins to climb permanently into the upper atmosphere, at around 650 million years from now. Others, using newer chemistry and newer plant physiology, push the collapse of the land biosphere out to something like 1.5, or nearly 1 9/10 billion years. The lead author of one of those newer studies, a young researcher named Graham working at the University of Chicago, has argued that plants may hold on much longer than we thought, until surface temperatures simply rise past the ceiling of photosynthesis and shut the chemistry down. The numbers are still moving. What is not moving is the shape of the answer. 1 billion, give or take. That is the honest window in which the Earth stops being a world that can hold anything complex, while the sun in its sky remains, to any outside observer, quietly and completely ordinary. The central question of tonight, then, is not the one we usually ask. It is not when the sun will die. It is something stranger. How does a living planet die while its star is still fine? How does the world go quiet under a sky that never even flickers? To feel the strangeness of it, you have to first feel how solid the present looks. And it is worth trying, just once, to feel how solid it looks, because everything that comes after depends on it. Consider the Pacific Ocean. It covers more of the Earth than all the continents combined, and it has been holding water for longer than any nervous system has existed to think about it. There are ridges beneath it that make new sea floor at the rate of a fingernail's growth, and trenches that swallow old sea floor back into the mantle. And in between there is a body of water so vast that light itself gives up in its upper hundreds of meters, and everything below is night. Consider the Amazon, 6.25 million square kilometers of forest, of which more than 5 million are still primary, untouched in the strictest sense, woven of trees that stand up out of a warm, wet air and pull carbon out of the sky by the ton. Consider Antarctica, 14 million square kilometers of ice, averaging nearly 2 kilometers thick, holding roughly 70% of the fresh water on the planet in a single cold, patient slab. If that ice melted, the sea would rise almost 60 meters, and every coastal city humans have ever built would go under. And yet that ice has been there, thickening and thinning at the edges but never truly leaving, for many millions of years. And consider us. Consider the whole human project, the cities strung along river mouths and coastlines, the 10,000 years of agriculture, the 6,000 years of writing, the 400 years of instruments carefully aimed at the sky. All of it built on the assumption that the sun will rise tomorrow at very nearly the strength it rose today, and that the year will have 4 seasons of very nearly the length they had last year, and that the average temperature of the world will drift only within the narrow band our crops and our cities can bear. The whole civilizational bet is a bet on the reliability of a single star. And here is the quiet, dizzying thing. The sun is not a fixed lamp. It has never been a fixed lamp. It looks fixed only because we are small and short-lived, and because the change we are measuring against is very, very slow. At the center of the sun, hydrogen is being fused into helium at a temperature of about 15 million degrees. The core, which is only a small fraction of the sun's volume, is where nearly all of that fusion happens, and at any given moment its composition is drifting. Today, it is roughly 35% hydrogen and 62% helium, when at the sun's birth it would have been overwhelmingly hydrogen. Every second, a small number of hydrogen atoms become helium, and helium is a heavier atom than hydrogen. That means the average particle in the core weighs a little more today than it did yesterday. It means, in the long, slow arithmetic of stellar structure, that the core has to contract very slightly to keep itself pressurized against the weight of the star above it, and when it contracts it warms, and when it warms it fuses a little faster, and when it fuses a little faster it shines a little brighter. That is the whole mechanism. There is no drama in it. It is one of the most patient processes in the universe, but its long consequence is enormous. Over the 4.5 billion years the sun has been on the main sequence, its luminosity has climbed by something close to a third. It shines today about 30% more brightly than it did when the Earth first cooled. Model calculations suggest it grows about 10% brighter every billion years. Extrapolated forward, in another billion years, the sun will be delivering something like 8% more energy to the top of our atmosphere than it does now. In 2 billion years, it will be roughly 20% brighter, and well before we ever reach the red giant, well before the outer envelope begins to swell, well before any of the theatrical late stages that documentaries usually save for last, the Earth will have stopped being able to keep its water. The rates are almost comically small on any timescale a human being can feel. From 1920 to 2020, an entire century of astronomical observation, the change in solar output was enough to raise Earth's average surface temperature by something on the order of 1/1,000,000th of a degree. That is the reason it looks like nothing. That is the reason the sun looks like a lamp. In a single century, in a single lifetime, in a single civilization, the change is undetectable in the noise of everything else the atmosphere is doing. But that quiet drift, extended over the long time scales that stars use, is the invisible hand already steering the Earth toward a different climate state. It is easy to forget how strange it is that this is happening at all. Everything else on Earth that has ever changed the climate has done so in the register of geology. Continents moving, volcanoes breathing, ice sheets advancing and retreating, ocean currents rearranging themselves as ridges rise and basins deepen. All of those things have their own rhythms and their own recoveries. The sun is different. The sun does not go back. Its brightening is one-directional. It is the only major driver of Earth's future climate that runs on a track from which there is no return, no feedback, no negotiating. And so, beneath the apparent permanence of the world, beneath the Pacific in its old bed, and the Amazon breathing its old breath, and the Antarctic ice in its long sleep, and the cities holding their bright grids together at the coasts, there is a slow, quiet, upward pressure on everything the sun touches. It has been there since before the first cell. It will be there after the last one. It is the closest thing our planet has to a fate. To understand what that fate means and to see why it feels so uncanny to look at the sun and know it is not staying still, it helps to go back to the beginning. Not to the middle of the story, to the moment before the story started, to the collapsing cloud out of which everything we are now made was first assembled. Return with me, one more time, to a place that had no name because there was no one to name it. 4.5 billion years ago, in a quiet, unremarkable arm of what would one day be called the Milky Way, there was a slow cloud of gas and dust, spread across a volume many light years wide, cold and thin and largely hydrogen. There was helium mixed in, the second most common element in the universe, and there were traces of everything else that older stars had made and released. Carbon and oxygen and iron and silicon in the tiniest of proportions, scattered as grains no larger than smoke. The cloud drifted and it turned, and for a long time nothing about it looked like the beginning of anything. Then some perturbation, the shock wave of a nearby supernova perhaps, or simply the slow inevitability of gravity acting on a cloud that had crossed some invisible threshold of density, set the collapse in motion. The cloud began to fall inward on itself. As it fell, it spun faster, the way a skater pulls in her arms, and as it spun, it flattened into a wide, slowly rotating disk with a thickening lump of gas at its centre. That centre was where the sun would be. The disk around it was where the planets would be. Time zero for our whole neighbourhood, the moment when the first solid grains condensed out of the cooling gas, is recorded in tiny inclusions inside certain meteorites. The calcium, an aluminum-rich flecks that geologists have dated, with astonishing precision, to about 4,567,000,000 years ago. At the centre, the pressure kept climbing. The core of the collapsing protostar warmed and warmed, and when it finally reached about 10 million kelvins, hydrogen fusion began. That is the moment we count as the sun's birth. From that point on, the young star settled into the main sequence, the long stable phase of stellar life on which it still sits, and began the very slow business of turning hydrogen into helium at its heart. But the sun that ignited then was not the sun we know. It was smaller in output. It shone, by the best estimates of stellar physics, at only about 70% of its current brightness. Cooler, dimmer, redder in its overall spectrum than the star that warms your window in the morning. If you could stand on the surface of the young Earth and look up through a sky no one would yet recognise, you would see a sun visibly, quietly weaker than the one your ancestors watched. And around that quieter sun, our planet was still being assembled. There was no Earth in the modern sense. There was a disk of dust and gas, and within it, over tens of millions of years, dust grains stuck to dust grains, and the resulting pebbles stuck to pebbles, and the resulting boulders drew in more boulders under their own weak gravity, until there were bodies the size of mountains, and then bodies the size of small worlds. These are the planetesimals, and Earth grew by eating them. Each collision brought heat. The gravitational compression of the growing body brought more heat. Radioactive decay in the deep interior brought still more. By the time Earth had assembled most of its final mass about 4.5 billion years ago, it was not the blue and green world we picture. It was a hot, glowing ball with much of its surface molten, its atmosphere still forming from the gases that outgassed from its interior, and the gases delivered by the endless rain of smaller bodies still arriving. Geologists call this earliest time the Hadean, from the Greek word for the underworld, and the name is fair in its early portion. There was very little that was cool or gentle about the first 50 or 100 million years of the planet. The moon-forming impact, in which a body roughly the size of Mars is thought to have struck the young Earth and thrown up the debris from which the moon would later coalesce, happened within this time. The heat from that collision alone would have remelted whatever crust had begun to harden. And later, perhaps 4 billion years ago, there is evidence in the ancient cratering record that the inner solar system endured a period of intense bombardment, a rearrangement of the giant planets' orbits, in some models, that flung asteroids inward for a stretch of tens of millions of years, hammering every young world within reach. And yet, and this is the part of the story that has puzzled scientists for half a century, the Earth of this early time was not frozen. It should have been. That is the thing that ought to stop us. A sun shining at 70% of today's output, delivering 70% of today's energy to the top of the atmosphere should, by every ordinary calculation of climate, have left the Earth's surface below the freezing point of water. Every ocean should have been ice. Every continent, had there been continents, should have been white. There is a straightforward physics of it. Less energy in, colder world. And yet the geological record insists otherwise. Tiny crystals of a mineral called zircon, some of them dated to as much as 4 4/10 billion years ago, tell us that liquid water was already present on the Earth's surface almost as early as the surface itself. They formed in conditions that required water, and they carry chemical fingerprints suggesting that surface temperatures at the time were probably below the boiling point of water and probably above its freezing point. By 3.5 billion years ago, and perhaps as early as 3 7 or 8/10, the first forms of life had begun to leave their marks in rocks, microbial mats, the chemical signatures of biology in ancient sediments, the microfossil record of things that ate and grew and reproduced in a warm, wet world. There were open oceans then, there were sunlit shallows. The sun that lit them was shining at something like 75, or 77, or 79% of its present brightness. The estimates converge in that band, and yet the seas did not freeze. This is the paradox that Carl Sagan and George Mullen first laid out. In a short and now famous paper in 1972, The Faint Young Sun Paradox. A dimmer star, a warm world, an energy budget that should not add up and yet somehow did. The most likely resolution then and now involves an atmosphere much richer in greenhouse gases than the one we breathe. More carbon dioxide, perhaps, and more methane, and different clouds. A thicker blanket catching more of the weaker light and holding it near the surface long enough to keep the water liquid. The details are still being worked out, and there is honest ongoing debate in the community about the exact mixture. But the fundamental shape of the answer is not really in dispute. The early Earth held itself warm by adjusting the properties of its own atmosphere against the faintness of its star. That fact, that the balance was, from the very beginning, an active balance, held together by the coupling of rock and water and air and light, is the thing to carry forward from this early chapter. Habitability has never been a static condition. It has never been something the planet simply inherited from the sun and then held in a jar. From the first day the Earth had a surface, its temperature was the result of a negotiation between the heat coming in from a still brightening star and the heat leaving through an atmosphere whose composition was being written and rewritten by weathering, by volcanoes, by oceans, by life itself, when life eventually arrived. The negotiation has been going on for 4.5 billion years. It is still going on tonight, and its terms quietly are shifting. In the beginning, the danger was that the sun was too faint, and the atmosphere had to compensate by holding the warmth in. That danger is long past. The sun kept brightening. The atmosphere over eons thinned in its greenhouse gases as living things pulled carbon into rock and into their own bodies. For a long stretch, including all of the stretch in which anything we would recognize as complex life has existed, Those two changes have run roughly in step. The sun has grown a little stronger, the greenhouse has thinned a little, and Earth's temperature has been held within the fluctuations of ice ages and warm periods inside a habitable band. But the two curves cannot stay balanced forever. The sun keeps brightening on its slow stellar track, and the greenhouse has less and less room to thin. There is a floor beneath the carbon dioxide in the atmosphere, set by the physiology of the plants that live on it, and there is a ceiling above the water vapour in the atmosphere, set by the physics of how much of it a warmer sky can hold before it starts leaking hydrogen into space. Somewhere ahead of us, in the long forward reach of that same negotiation that has kept Earth habitable since the Hadean, the terms shift beyond what any thermostat we know can compensate for, and that is where the story of the deadline really begins. Not with anything dying, not with any catastrophe, only with the same quiet drift of an ordinary star that has been operating since before there was anyone to feel it, continued into a future in which the balance no longer holds. There is a long chapter still to come between here and there. The chapter of the thermostat that kept us safe, and the chapter of the oxygen world that changed everything, and the chapter of the water that will slowly, patiently climb into the sky. And there is at the end a chapter about ourselves, about the odd, brief position of being the one species that seems to know, however dimly, what the clock says. For now, it is enough to sit with the strangeness of the opening. The sun in the sky at this moment is not the sun that lit the Hadean, and it is not the sun that will light the last ocean. It is a star in mid-life, faithful in every way that stars are faithful, and quietly, invisibly, imperceptibly on the move. The world beneath it is only as still as our short lives make it look. It is worth returning for a while to the moment when the world first cooled enough to keep its own weather. The Hadean did not end in a single afternoon. It thinned. The bombardment slackened. The last great impacts scattered themselves further and further apart in time. The surface, which had spent hundreds of millions of years being reworked by heat from below and by projectiles from above, began, at last, to hold its shape. Somewhere around 4 billion years ago, by the reckoning geologists have pieced together from the oldest rocks that still survive at the surface, the Earth crossed a threshold that had nothing dramatic about it. The magma oceans were long gone. The crust in patches had been solid for longer than any of us can quite imagine. But now the impacts thinned, and the sky cleared, and the clouds, which had condensed and rained and evaporated and condensed again through every earlier crisis, settled into something more like a permanent ocean. That threshold is the door into the Archean. It was a very long eon. It ran from about 4 billion years ago to 2.5 billion years ago, and that stretch alone accounts for something close to a third of the entire history of the Earth. Almost everything that would eventually make our world was invented in it. Quietly, under a dim sun, in an atmosphere that would have killed anything we know. If you sorted our planet's story by duration, and you asked which chapter was the longest, the Archean would answer without contest, and yet it left almost no monuments. The rocks are old and few. The organisms were small and soft and mostly microbial. The continents were still assembling themselves. Whole hundreds of millions of years pass in the Archean with almost nothing to show for them but a scatter of altered sediments and a handful of chemical fingerprints. The eon is enormous, and from the surface nearly featureless, which is, in its way, a fair description of the surface itself at the time. The sun at the start of the Archean was still faint. It was giving Earth something like a fifth less light than it does tonight, and by any straightforward calculation, that should have been a killing shortfall. The planet with a modern atmosphere and modern reflectivity would have frozen from the poles inward and stayed frozen. It did not. The rocks are patient witnesses to that fact. Sedimentary layers laid down under liquid water at 3.5 billion years ago, mudstones and cherts and the layered mounds we call stromatolites, all evidence of a world in which the seas were not only unfrozen but, in places, decidedly warm. Some proxies place the ocean temperatures of the mid-Archean somewhere between 55 and 85 degrees Celsius, the temperature of a hot bath or hotter, although the interpretation of those proxies is still debated. Even taking the coolest reasonable estimates, the Archean was not an ice-locked world. It was a wet, warm world that had no business being warm, given the sun above it, and the reconciliation of that mismatch is one of the quietly great achievements of the last half-century of geoscience. The answer, or a great part of the answer, sits inside the composition of the Archean atmosphere itself. It was a strange sky, by our standards. There was no free oxygen in it. There was instead a great deal of nitrogen, and a great deal more carbon dioxide than we have now, somewhere from 10 times modern amounts at the low end of the estimates, up to a couple of thousand times at the high end. And there was methane. The methane numbers, as best as the proxies allow, are staggering. Perhaps 100 times, perhaps 10,000 times the trace amount we carry today. Alongside these there were smaller quantities of carbon monoxide, of molecular hydrogen, a whole reducing chemistry of gases that would today be either scrubbed out within years or set on fire by the first passing spark. The Archean atmosphere was not a poisoned version of our own. It was another sort of atmosphere entirely, held in a different chemical balance, keeping a different kind of warmth in beneath a fainter star. That much greenhouse, that much heat trapping would have been intolerable under the sun we know. Under the sun the Archean knew, dim and slowly climbing, it was exactly enough. The mismatch that would otherwise have frozen the world was made up for by an atmospheric blanket thick with the very gases that a modern Earth spends so much effort keeping thin. It is one of the oldest lessons in planetary science, and it is worth pausing on. The same gas can be salvation or catastrophe, depending only on the star above it and the balance beneath. The blanket, however, was not merely thrown on and left. It was managed. That is the astonishing part. There was, buried inside the geology of the young Earth, a mechanism that could, over long enough stretches, take too much carbon dioxide out of the air when the world grew too warm, and put too little back when the world grew too cold. It was slow. It was clumsy. It did not respond within a lifetime or a millennium, or often even within 100,000 years. But over the immense stretches of time that geology deals in, it worked, and it kept working, and it is arguably the single most important reason there is anyone here to speak of it. The mechanism is called the carbonate-silicate cycle, and its parts are absurdly ordinary. The Earth has silicate rocks, vast masses of them in every continent, in every ocean crust, in every mountain range. It has an atmosphere with carbon dioxide in it. It has rain. When rain falls through the air, carbon dioxide dissolves into it, making a very weak carbonic acid. When that faintly acidic rain touches exposed silicate rock, the rock, over time, breaks down. The chemistry is patient and unglamorous. Atoms of calcium and magnesium, freed from the crystals, wash off with the runoff, carrying the dissolved remains of atmospheric carbon dioxide with them. The rivers deliver those ions to the sea. In the sea they combine with dissolved carbon to make carbonate minerals, which sink to the ocean floor as a slow, endless drizzle of chalk and shell and mud. And there, on the sea floor, the carbon dioxide that started in the atmosphere is now locked in stone. That would be the end of the story, and the atmosphere would eventually be scrubbed clean if the cycle did not close. But the sea floor is not a graveyard. It is a conveyor. It slides, over tens and hundreds of millions of years, toward the deep trenches where one plate dives beneath another. In those trenches, the carbonates ride the descending crust downward, into pressures and temperatures at which the carbon they carry is cooked back out of them. It rises again, through cracks and vents and volcanoes, and re-enters the atmosphere as gas. The cycle is closed. Carbon dioxide leaves the air through weathering, is stored in stone, is returned to the air through volcanism. The whole loop takes millions of years to complete a single circuit. And yet somewhere inside that slow loop, there is a thermostat. The thermostat works because rain does not simply happen. Rain is a function of temperature. A warmer world is a wetter world. Warmer air holds more water vapour. A warmer surface evaporates more of the sea, more evaporation feeds more clouds and ultimately more rain. If for any reason the Earth grows warmer, a spasm of volcanism, a change in continental configuration, a shift in the reflectivity of the surface, the increased warmth intensifies the whole hydrological cycle. More rain falls on more rock, more silicate is weathered, more carbon dioxide is pulled out of the atmosphere and washed into the sea, and with less carbon dioxide overhead, the greenhouse effect thins and the planet cools. If, on the other hand, the Earth grows colder, the reverse begins. Rain slackens, weathering slows. Carbon dioxide, still being emitted by volcanoes at whatever their steady rate happens to be, accumulates in the air faster than it can be scrubbed out. The greenhouse thickens, the planet warms. It is a negative feedback of the simplest, most elegant kind. Warmth invites its own removal, cold invites its own reversal. The mechanism does not care what is causing the warming or the cooling. It does not need to know. It only needs the rain and the rock and the volcanoes to keep doing what they do, and over the long enough term the atmosphere adjusts. The Archean Earth, under a sun still faint but slowly climbing, sat inside exactly such a slow adjustment. As the star grew brighter over hundreds of millions of years, the surface would have warmed a little. The warming would have intensified the water cycle. The intensified water cycle would have quickened the weathering. The quickened weathering would have drawn down atmospheric carbon dioxide. The greenhouse would have thinned in step with the brightening star, and Earth's temperature, averaged over the 10 million year timescales the geology can resolve, would have stayed inside a habitable band. This is the thermostat. This is why the ocean did not freeze under a 20% dimmer sun. This is why the ocean did not boil when the sun eventually finished its climb. And it is a thermostat that no one designed and nothing intended. It is the accident of chemistry that happens when a rocky planet has silicate rock and liquid water and a working carbon cycle and enough tectonic life to keep the crust turning over. Every part of the loop was, and is, indifferent. The rock does not know it is regulating the sky. The rain does not know it is cooling the world. The volcano does not know it is completing a circuit. And yet the loop closes, and the world stays warm, and the ocean stays wet for 4 billion years and counting. There is a detail here that is easy to pass over, and it is the detail that will matter most in the chapters ahead. The thermostat has direction. It is very good at pulling carbon dioxide out of a warming atmosphere. It is much less good at pushing it in when there is no more to push. There is a flaw. The volcanoes do not stop. Carbon dioxide is always being returned to the sky. But the weathering runs faster than the return whenever the world grows too warm, and slower than the return whenever the world grows too cold, and the equilibrium, the balance point at which the two rates match, has been sliding gently downward for a very long time. The Archean atmosphere had, at the low end of the estimates, 10 times as much carbon dioxide in it as ours does. The Proterozoic atmosphere had less. The Phanerozoic, the last 500 million years, in which every animal that has ever lived has had less again. The trend, averaged across the great sweep of the geological record and setting aside the short human present entirely, has been the same trend for eons. Down. Less carbon dioxide overhead, a thinner greenhouse, a cooler planet than the sun of the moment would otherwise produce. And that is not a coincidence. It is the thermostat, doing its slow, patient work, drawing the greenhouse down as the star climbs. But the greenhouse cannot draw down forever. There is a flaw beneath the carbon dioxide, and the flaw is not set by the rock or the rain. It is set by the living things that use the gas to build themselves. Plants, and the algae that came before plants, need carbon dioxide the way animals need oxygen. Below a certain concentration, the enzymes that assemble the sugars of photosynthesis simply cannot find enough of it to work with. The lights go out at the cellular level. When the atmospheric flaw of carbon dioxide reaches that threshold, the thermostat can pull no further, because there is nothing more to pull without also unmaking the biosphere. That is the seed of the future catastrophe, buried inside the mechanism that has kept us safe. The same loop that saved the Archean world from its faint sun is the loop that will one day run out of room to save a future world from its bright one. But we are not there yet. In the Archean, the floor was very far away. There were oceans of carbon dioxide overhead, in every sense that counts. The thermostat could sink a very great deal before it began to hit anything, and into that steady, self-adjusting, carbon-thick world, at some point in the Archean and possibly earlier, life had arrived. The earliest microbes were prokaryotes, single cells without nuclei, without any of the elaborate internal machinery that eukaryotic cells would later carry, but with everything they needed to survive in an anoxic, mildly acidic, moderately warm world. The fossil evidence for them goes back extraordinarily deep. There are structures in rocks around 3.5 billion years old, and, on more contested readings, closer to 3.7, that appear to be the remains of microbial mats, layered communities of cells, glued together on the floor of shallow seas, alive and eating and dividing. The organic laminae inside the stromatolitic carbonates of that age are the ghost of those mats, pressed flat by 3 billion years of overlying sediment. Whatever they were, precisely, they were alive, and they were already doing what living things do, pulling atoms out of the environment and rearranging them into more of themselves. Some of those early microbes were methanogens. They took hydrogen from the water, carbon dioxide from the air, small organic molecules from wherever they could find them, and they made methane as a waste gas. The chemistry is ancient. The archaea that still perform it today are among the most primitive branches on the tree of life, and their metabolism appears to have been in place, in some form, more than 3 billion years ago. Every cell of a methanogen is a tiny factory venting methane into the world around it, and in the Archean there was no free oxygen anywhere to react with that methane and destroy it. It accumulated, it thickened. The methane in the Archean atmosphere, produced in unknown but very large quantities by these unseen microbial factories on the sea floor, is thought to have been a significant part of the greenhouse blanket that kept the young Earth warm. Consider what that means for a moment. The thermostat that we have been describing, rock and rain and volcano, was a purely geological device. It did not need life to function. It would have worked on a sterile world. But by the middle of the Archean, life had joined the thermostat. The microbes were adding methane to the atmosphere, thickening the blanket, keeping the ocean warm. Somewhere else in the same seas, other organisms were beginning to experiment with photosynthesis, first probably in forms that did not release oxygen at all, that used hydrogen sulfide or dissolved iron as their source of electrons, and only later, at some point around 2.9 billion years ago, in the form that would change everything. Life was already, quietly, becoming a geological force. The stones and the seas would keep negotiating the temperature of the earth with the sun, as they had from the beginning. But there were now living things at the table, and through all of this the continents were slowly assembling. The Archean was the great age of continent building, somewhere between 3 billion and 2.5 billion years ago. In a stretch of a few 100 million years, roughly 70% of the total continental crust that exists on the Earth today was formed. Cratons, the ancient stable hearts of the continents, solidified across the planet one after another in a spasm of crust formation whose exact causes are still argued over. Greenstone belts laced with gold and silver laid themselves down through what would eventually become Western Australia and Southern Africa and the shield of central Canada. Island arcs collided and welded. The planet, which had begun the eon with almost no dry land, ended it with the raw materials of every future continent already in place, waiting to be shuffled by tectonics into the arrangements we know. This mattered, in its slow way, for the thermostat. More continental crust exposed to weathering meant more silicate rock in the rain. More silicate rock in the rain meant a more responsive drawdown of carbon dioxide. The regulatory power of the whole system depends in part on how much rock the rain has to work on. The Archean built the continents that would run the thermostat for the rest of Earth's habitable life. It was, in that sense, laying the machinery for its own successors. And then the machinery was pushed, somewhere near the end of the Archean, around 2.5 billion years ago. The atmosphere itself began to change in a way that would alter everything. The eon closed with the first substantial rise of oxygen in the air. That rise had, in a sense, been coming for hundreds of millions of years. Cyanobacteria, the specific group of microbes that had, at some point earlier in the Archean, worked out how to split water molecules to power photosynthesis, had been quietly releasing oxygen as a byproduct for perhaps 500 million years before it started to accumulate anywhere it could be measured. The molecule was, from the cyanobacterial point of view, a waste product. It was not something the organism wanted. It was corrosive. It was reactive. It had to be discarded for the cell to survive. But the cell survived, and it discarded, and it kept discarding, generation after generation, in whatever shallow, sunlit stretches of the Archean Sea it could colonize. And for a very long time the discard vanished as fast as it was made. The oceans were full of dissolved iron, hungry for oxygen. The rocks of the seafloor were reduced, hungry for oxygen. The gases of the atmosphere were reduced, hungry for oxygen. Every molecule of it that a cyanobacterium released was seized by some other molecule waiting to react with it, and none of it made it into the sky. Then, at some point in the interval that runs, on the tightest current estimates, from about 2,501 million years ago to about 2,434 million years ago, the balance tipped. Whether it was that the sinks finally filled, that the iron in the sea was oxidized to rust and settled out into the great banded iron formations that still stripe the rocks of that age, or that the cyanobacteria became abundant enough that their output finally exceeded the appetite of the world beneath them, or both, the effect is not in doubt. Oxygen began to accumulate, not to modern levels, nothing close, but from essentially none to a measurable trace, and then a little more, and then enough to leave chemical fingerprints in every sediment laid down afterwards. The Archean atmosphere, with its methane and its carbon dioxide and its reducing chemistry, gave way over a couple of 100 million years to something new. The Earth entered what is now called the Great Oxidation Event, and the transformation, on the scale of the whole planet, was as thorough as anything that has happened before or since. The immediate consequences were, for the Earth of that moment, largely bad. The methane that had helped keep the Archean warm reacts readily with oxygen. As the oxygen rose, the methane fell, and one of the great pillars of the Archean greenhouse was pulled out from under the sky. The world, in the aftermath of the oxygen rise, appears to have plunged into one of the deepest cold snaps in its history, a global glaciation, perhaps a snowball state, running from roughly 2.3 to 2.2 billion years ago, in which ice reached in some reconstructions all the way to the equator. The rise of oxygen and the fall of temperature are almost exactly contemporaneous, and the causal link between them, though still argued over in its details, is one of the most striking coincidences in the geological record. The first great gift of life to the atmosphere may also have been the first great climatic disaster of the planet. And yet the ice retreated in time, and the atmosphere held its new oxygen, and everything that came afterward flowed from that change. It would take another 2 billion years for the concentration to climb toward anything like modern values, and there were long stretches, much of the middle Proterozoic, when the oxygen level appears to have been stuck at a small fraction of what we breathe. But the ceiling had been raised. The atmosphere was, for the first time in the planet's history, an oxidizing one. And that fact, once established, would rewrite the rules of what was possible on the surface of the Earth. Somewhere in that transformation, and not exactly synchronized with it, eukaryotic cells appeared. Cells with nuclei, with organelles, with the interior architecture that would eventually make every plant and animal and fungus possible. The timing does not line up cleanly with the atmospheric transitions. The origin of eukaryotes seems to precede the deep oxygenation of the oceans by a very long stretch, but the ecological space that oxygen opened, The possibility of an aerobic metabolism that could extract far more energy from food than any of its anaerobic predecessors was the space in which those larger, more complex cells would eventually flourish. Every cell in your body today is a eukaryotic cell. Every one of them runs on the aerobic chemistry that the great oxidation event made possible. Every mitochondrion inside them is the descendant of a bacterium that once thrived on the very molecule the cyanobacteria were throwing away as garbage. The waste product became the fuel of every animal that has ever lived. Above the oceans, in the sky, another consequence of the oxygen was taking shape. Some of the oxygen molecules high in the upper atmosphere were being split by ultraviolet light and recombining into ozone. Ozone in trace amounts is nothing much. Ozone in a thin, high-altitude layer is a shield. It absorbs the shortest and most damaging wavelengths of the sun's ultraviolet output, the wavelengths that shatter the bonds of proteins and the strands of DNA, and it turns them into heat before they can reach the surface. Without an ozone layer, the land is a killing floor for anything more complicated than a bacterial mat. With one, life can, in time, come ashore. The ozone shield built up gradually, tracking the rise of oxygen through the Proterozoic and into the Phanerozoic, and by around 600 million years ago, on the best current estimates, a thin ozone layer had formed that was capable of screening out the most lethal parts of the ultraviolet spectrum. By around 420 million years ago, in the Silurian, ozone concentrations were high enough that the surface of the land could be inhabited by anything more than the intertidal fringe. The first colonists were probably algae and fungi, then the first small vascular plants, then, eventually, the ancestors of everything that walks and flies and burrows on land today. It took 2 billion years from the first accumulation of atmospheric oxygen to the first forests. It took another 400 million from the first forest to us. All of it, every step, rests on the same narrow chemical arrangement. A sky with the right amount of oxygen in it, an ozone shield above, a carbon dioxide concentration low enough to keep the greenhouse in check, and high enough to keep the plants alive, and, holding the whole thing together against the steady climb of the star, a thermostat of rain and rock that has been quietly running for 4 billion years. The world every large animal inhabits is not a default. It is a specific arrangement, held in place by living things that make oxygen, and by mineral processes that regulate carbon, and it exists only in the narrow band where all of those balances happen to overlap. That overlap is what will begin, in the chapters ahead, to narrow. And so we come at last to the present hour and to the star itself. It is very easy to forget, standing under a summer sky, that the sun is a thing in progress. It looks like a fixed feature of the world, the one utterly reliable object in every human life, rising and setting on a schedule no calendar has ever had to correct. Nothing about it, to the eye, suggests change. Nothing about it, in any single human lifetime, actually does change in any way we can feel. And yet the sun is not the sun it was when the first stromatolites were laid down in shallow Archean water, and it is not the sun it will be when the last drop of the last ocean lifts from the last sea floor. It is a slowly evolving object. It has been evolving since the moment it first ignited, and the evolution has always been in one direction, and the direction is toward more. The physics of this is not mysterious, and it is not in doubt. It has been worked out, checked, and rechecked by generations of astrophysicists, and confirmed by instruments the Archean world could not have imagined. In the core of the sun, at a temperature of about 15 million degrees and a pressure so extreme that matter behaves in ways that have no equivalent on any planet, hydrogen is being fused into helium. The reaction proceeds through what is known as the proton-proton chain, a slow, patient sequence in which 4 protons, one small step at a time, are turned into a single nucleus of helium-4. In the process, a small fraction of the original mass is released as energy, and it is that energy, worked outward through hundreds of thousands of years of scattering and reabsorption in the radiative zone, and then carried up through the churning convection zone above, that eventually reaches the surface and streams out into space as sunlight. Every photon that warms your face on a spring afternoon was born, in a sense, in that slow arithmetic of protons deep in the solar core and travelled a long, dark road before it ever met the sky. Every second, the sun turns roughly 600 million tons of hydrogen into helium. Of that, about 4 million tons vanish as energy, streaming outward in all directions. The rest accumulates as helium ash in the core. That last phrase is easy to pass over, and it is the phrase that contains the deadline. The helium is not a waste product that gets swept away or recycled. It stays where it is made. It gathers in the innermost region of the sun, denser than the hydrogen it replaces, and it changes slowly. The conditions under which the fusion is taking place. The consequence of that accumulation is the entire story of this documentary compressed into a single sentence of physics. As helium builds up, the core contains fewer particles for the same amount of mass, because each helium nucleus is heavier than the 4 protons it took to make it. Fewer particles means less pressure at a given temperature, and less pressure cannot hold the weight of the star above. So the core contracts very slightly under its own gravity. When gas contracts, it heats. A hotter core burns its hydrogen faster, and a faster fusion rate means more energy released, and more energy released means a brighter sun. That, in essence, is why every main sequence star grows brighter over its lifetime. It is not a defect of the sun. It is a feature of every star that lives by fusing hydrogen at all. The sun began its life on the main sequence with a core that was about 71% hydrogen. Today, 4.5 billion years later, that number is down to roughly 34%. More than half of the hydrogen that was originally in the core has already been converted into helium. Over the same interval, the sun's luminosity has risen by close to a third. The sun that shines on us now is not the sun that shone on the earliest oceans, or the first cyanobacteria, or the first forests. It is a brighter, hotter engine, running through the same fuel but running it faster. The rate at which this brightening continues is roughly 10%. For every billion years, the sun remains on the main sequence. Different models, using different assumptions about interior mixing and metallicity, give values that range from about 8 to about 10% per billion years. But all of them agree that the trend is upward and that the trend is inexorable. It is not a cycle, and it is not a phase. It is the ordinary aging of an ordinary star, and it will not turn around. We know this because we can look inside the sun. Not with our eyes, of course, and not with any instrument that peers through the photosphere as through a window, because the interior of the sun is opaque to light the whole way down. But the sun is not silent. Its surface is in constant subtle motion, oscillating in a pattern of ripples that repeat, on average, every 5 minutes or so. Those oscillations were first noticed in 1962 by Robert Layton and his colleagues Robert Noyes and George Simon at the observatory on Mount Wilson. In a study that at first looked like an odd anomaly in the surface velocities, it took another decade or so before their meaning became clear. The 5-minute oscillations are acoustic waves, sound waves, trapped inside the sun. They are set going by the turbulence of the convection zone, and they ring the whole star as a struck bell rings after the mallet. And like the tones of a bell, they carry information about the shape and the composition of the object that produced them. The science of listening to those tones is called helioseismology. It works by measuring the tiny Doppler shifts in the light from the solar surface as different regions rise and fall in the oscillations, and by extracting from those shifts the frequencies at which the sun most naturally rings. Those frequencies depend on the temperature, the density, and the composition of every layer the sound waves pass through. From a careful catalogue of the modes, patient teams of astrophysicists have reconstructed the internal structure of the sun with a precision that would have astonished anyone born in the 19th century. The temperature at every depth, the pressure, the density, the composition, the rotation rate, layer by layer, the location of the boundary between the radiative and convective zones, all of it inferred from the ringing of the star's surface, all of it consistent to within a fraction of a percent, with the models built from the physics of fusion. And what heliosismology confirms is exactly the picture the theory demanded. There is a core of hot helium-rich plasma at the centre, contracting slowly, brightening slowly. There is a shell of hydrogen fusion around it. There is a radiative zone above that, in which the energy diffuses outward as radiation. There is a convection zone above that, in which the energy is carried by boiling motions of hot plasma. The interior of the Sun is not a mystery. It is a place we have mapped without ever going near it, by listening to the sound of it moving. A second, entirely different confirmation came from below, from the strangest particles the Sun produces. When 4 protons fuse to form a helium nucleus in the proton-proton chain, the reaction releases neutrinos, ghostly, nearly massless particles that interact with matter so weakly that most of them stream straight out through the body of the star, through the intervening space, through the Earth, through you without noticing any of it. If the fusion is happening in the core at the rate the models say, then neutrinos of specific energies must be pouring out of the Sun in vast numbers. Detecting them requires instruments buried deep beneath mountains, shielded from every other kind of radiation, and staring for years at tanks of ultra-pure liquid. For a long time, the neutrino counts came in mysteriously low, and the puzzle of the missing solar neutrinos hung over the physics of the Sun for decades. It was eventually resolved, not by any error in the solar models, but by a subtle property of the neutrinos themselves, which change identity as they travel. In the years that followed, experiments went further. The Borexino detector in Italy's Gran Sasso laboratory confirmed in exquisite detail the different steps of the proton-proton chain, culminating in a 1962-style identification in 2014 of the neutrinos from the very first step of the reaction, the low-energy neutrinos that only the beginning of the PP chain produces. That measurement closed a circle that had been open for half a century. The energy the Sun is emitting today matches the energy the fusion in its core is generating today. The Sun is running as advertised. The models are right. The brightening is real, and the brightening will continue. None of this, of course, is felt. Over the last century, from 1920 to 2020, the change in solar output has warmed Earth by something on the order of a millionth of a degree. It is not a temperature change any thermometer will ever record, and it will never be noticed by anyone who lives through it, because it is drowned out completely by the noise of ordinary weather and the far larger perturbations we ourselves have introduced by other means. A million years from now, the accumulated increase will still be well under 1/10 of a degree from solar brightening alone, and yet the direction never reverses. There is no negative feedback in the core of a star that undoes the accumulation of helium. There is no mechanism by which the ash of fusion becomes fuel again. The graph, plotted over the age of the Earth, is a nearly straight line rising very slowly to the right, and it never bends downward. This is the menace at the heart of the story, and it is a menace unlike any the imagination usually reaches for. It is not an asteroid, whose approach can in principle be plotted and in principle deflected. It is not a supernova next door or a nearby gamma-ray burst or a wandering black hole. It is nothing sudden. It is the ordinary aging of the ordinary star that stands at the centre of everything we have ever built, changing so slowly that no living thing on the planet can perceive the change in real time, and so powerfully that Earth cannot indefinitely absorb it. There is no drama in it. There is no announcement. There is only a graph and a slope and a value at which certain thresholds are crossed. The first of those thresholds involves water. Water is peculiar among substances. It is a small molecule, 3 atoms, and it exists on our world in all 3 of the classical phases or ordinary temperatures, as vapour in the air, as liquid in the oceans and the rain, as ice at the poles and on the mountains. It is also a greenhouse gas, and a stronger one, molecule for molecule, than carbon dioxide. It absorbs infrared radiation across a broad band of wavelengths, and it is the largest single contributor to the greenhouse effect on Earth today, responsible for roughly half of the warming that keeps our planet from freezing. The amount of water vapour the atmosphere can hold, however, depends very strongly on temperature. This is not a matter of policy or chemistry that could be adjusted. It is the Clausius-Clapeyron relationship, one of the oldest and most reliable results in thermodynamics. For every degree Celsius of warming, the atmosphere's capacity to hold water vapour increases by about 7%. Warmer air is thirstier air. A warmer surface evaporates its oceans faster, and the warmer atmosphere accepts the extra vapour without complaint, and the extra vapour, being itself a greenhouse gas, warms the surface still further, which drives more evaporation, and so on. It is a positive feedback loop, and it more than doubles the warming that carbon dioxide alone would produce. On the Earth of today, this feedback is stable. It amplifies temperature change, but it does not run away, because there is a lid on the whole process high in the atmosphere. Above the weather layer in the region called the stratosphere, temperatures drop to a minimum at the boundary called the tropopause, and moist air rising from below encounters the cold band and dumps its water out as ice or rain long before it reaches the higher altitudes. The stratosphere, as a result, is extraordinarily dry. This atmospheric cold trap, as it is called, is what keeps Earth's water where it belongs. Water vapour that never reaches the upper atmosphere is water vapour that cannot be lost to space. It falls back to the surface as rain, on average within about 9 days of evaporating. The oceans, in effect, are held down by a lid of cold air. The question is what happens to that lid as the sun grows brighter. The most influential answers came from a line of research begun in earnest in the 1980s by James Casting, then working on the problem of habitable zones around sun-like stars, and refined in a 1993 paper published in the journal Icarus. Casting and his colleagues formalized the notion of a moist greenhouse state, a condition in which the surface has warmed enough and the atmosphere has moistened enough that the stratospheric cold trap fails. Water vapour in that state is no longer confined below the tropopause. It works its way up into the high atmosphere, where the pressures are low and the ultraviolet flux from the sun is high. There, ultraviolet photons split the water molecules apart. The reaction is simple enough to write in a single line. 2 molecules of water plus a photon of ultraviolet light yield 1 molecule of oxygen and 4 hydrogen atoms. The oxygen is heavy enough to stay bound to the planet. The hydrogen is not. Hydrogen, at the top of the atmosphere, is light enough that a small but significant fraction of the molecules will always have velocities in excess of Earth's escape speed. It slips away into space, 1 atom at a time, in a slow leak that thermodynamics does not permit us to close. The threshold in Casting's original models was set around a surface temperature of about 350 Kelvin, roughly 77 degrees Celsius as a global mean. Above that temperature, the stratospheric water content rose so steeply that the cold trap was overwhelmed and the loss of hydrogen became geologically significant. Later work, using more sophisticated 3-dimensional climate models, sharpened these numbers and in some cases moved them. A key result from more recent modelling suggests the tipping point for ocean evaporation lies around a mean solar flux of roughly 375 watts per square metre, compared to the present-day value of about 341, and that this level is reached in something close to 1 billion years. Other 3-dimensional simulations have suggested that the climate may remain safe against both water loss and thermal runaway for at least another 1.5 billion years, especially once the cloud responses of a warming planet are treated more carefully. The estimates range across nearly a factor of 2, and different assumptions about clouds, about atmospheric circulation, about the response of the biosphere, shift the numbers up or down by hundreds of millions of years. But the direction is the same in every model. Sooner or later the cold trap fails, and once it fails the ocean begins to leave the planet by way of the sky. The imagery this deserves is not one of a boiling sea, it is nothing so dramatic. The oceans in this scenario do not vanish in a single lifetime, or in 10,000 lifetimes. They do not visibly diminish over any span of history a civilization could witness. What happens instead is that the stratosphere becomes a little damper each geological epoch than it was the epoch before. The hydrogen mixing ratio at high altitudes rises past a threshold. 1 part in 1,000 is the rough figure at which the loss rate becomes serious. 1 part in 100 is the point at which the process runs freely. And above the cold trap in the thin air where sunlight cuts and splits, a slow bleed begins. The rain still falls, the clouds still gather, the tides still turn. But the total inventory of water, integrated over the whole surface and atmosphere, ticks downward by a fraction of a fraction each 1,000 years, and it never ticks back up. Earth begins to lose its ocean not in one dramatic boil, but molecule by molecule from the top of the sky. Even before that stage is fully reached, though, another balance will already have broken, and the balance that breaks first is the very one that has kept the planet habitable for 4 billion years. The carbonate-silicate cycle, that patient thermostat, has always worked in a particular direction. When the surface is warmer, silicate rocks weather faster. Rainwater, faintly acidic with dissolved carbon dioxide, reacts with the silica in exposed rocks and breaks them down into dissolved bicarbonate. Rivers carry the bicarbonate to the sea, where marine organisms use it to build shells of carbonate, and when they die, the shells fall to the sea floor and are eventually locked into limestone. Carbon dioxide in this cycle is drawn out of the air by warmth and stored in stone. On the other side of the ledger, volcanoes, and to a lesser extent metamorphic reactions in the crust, quietly release carbon dioxide back to the atmosphere at a rate of roughly 1/10 of a petagram of carbon per year, a flux small enough to be dwarfed by human emissions in the present epoch, but over 1 million years, enough to nearly triple the combined carbon inventory of the atmosphere and the ocean. For most of Earth's history, weathering and volcanism have balanced each other, and the balance has moved obligingly in whatever direction the sun's slow brightening required. When the sun was faint, weathering was slow and the atmosphere held more carbon dioxide and the greenhouse effect was strong. As the sun brightened, the surface warmed a little, weathering quickened, and carbon dioxide was drawn down, and the greenhouse effect weakened by just enough to keep the temperature within tolerable bounds. It is an extraordinary arrangement, running for eons, self-adjusting, self-correcting, but it has a flaw. Carbon dioxide cannot be drawn down indefinitely, because the plants that carry out photosynthesis on land are themselves consumers of it, and they cannot survive below a certain concentration. The dominant kind of terrestrial photosynthesis, the C3 pathway that operates in about 85% of vascular plants, in the trees of every forest, in the wheat and rice and soybeans of every farm, has a compensation point around 150 parts per million. Below that concentration, C3 plants cannot photosynthesize fast enough to offset their own respiration, and they enter a state of negative carbon balance, in which they burn through their stored tissues and starve. The evolutionary latecomers, the C4 plants, which use a biochemical trick to concentrate carbon dioxide around the enzymes of photosynthesis, can hold on considerably longer. Their threshold is around 50 parts per million. But even they have a flaw, and below it they too fail. As the sun brightens, the carbonate-silicate cycle draws the atmospheric carbon dioxide steadily downward. It does this because the physics of weathering demands it. A warmer surface weathers faster, and faster weathering means faster drawdown, and the volcanoes cannot keep up. There is no negotiation in the chemistry, and there is no reserve to draw upon. Somewhere, on a schedule set by the slope of the solar luminosity curve and the temperature dependence of silicate weathering, the atmosphere's carbon dioxide falls below the C3 compensation point, and then, after another long stretch, below the C4 compensation point. Long before the oceans have significantly diminished, and long before the surface temperature has climbed to anything a human would find intolerable, the plants of the land will simply run out of the gas from which they build their bodies. The consequences ripple outward with the quiet inevitability of the rest of the story. Forests thin, then fail, standing dead where they grew. Grasslands hollow out. their productivity falling to values that cannot support the animals that graze them. The herbivores decline, and the carnivores that depend on the herbivores decline in their turn. The webs of interdependence that built themselves up over 400 million years since the first small vascular plants took hold in the Silurian mud come apart in a sequence that no living observer will be there to witness. There is no reversal in this. There is no rescue. The sun does not dim, the weathering does not slow, the volcanoes do not learn a new trick. The thermostat that held the world in habitability for 4 billion years finally fails not by breaking, but by doing exactly what it was always doing one last time past a limit it could not know it had. And all of this begins to unfold long before the ocean itself has meaningfully begun to leave. The first great loss is not of water. It is of green. It is worth pausing on what that loss actually looks like when it comes, because the word extinction, worn smooth by long use, does not quite carry the shape of it. The end of the green world is not a moment. It is not a season, or a century, or even a geological instant of the sort a stratigrapher might find as a thin dark line in some future rock. It is a drawn-out ebbing, a leaching of colour and productivity from the surface of the planet across tens and hundreds of millions of years in a sequence set by the different tolerances of different lineages, and it begins not with catastrophe, but with something far more ordinary. It begins with plants that seem, by every visible measure, to be doing exactly what they have always done, and yet are quietly falling behind. The C3 plants go first, because they are the majority, and because their machinery is the older and less clever machinery. Their photosynthesis is straightforward. A leaf opens its pores in the morning, carbon dioxide diffuses in, an ancient and slightly clumsy enzyme called rubisco fixes it into a 3-carbon molecule from which the rest of the plant substance is built. The whole arrangement works beautifully in an atmosphere rich in the gas the enzyme is fishing for, and it works less and less well as that gas grows scarce. Long before the compensation point is reached, long before the plants actually starve, they begin to lose efficiency. In the record of the recent past, this has already been glimpsed. As atmospheric carbon dioxide drifted downward across the last 30 million years or so, C3 plants across whole continents suffered a measurable decline in the efficiency of their carbon fixation, and at higher temperatures the effect grew sharper, reducing photosynthesis by nearly a quarter in some regimes. In Earth's ice ages, when carbon dioxide fell to around 180 parts per million, C3 vegetation was already visibly under strain, the forests smaller, the productivity lower, the growing seasons more marginal. These were only visits toward the floor. The long future brings a permanent approach to it, and so the first signs, in the imagined slow motion of that distant epoch, are not fires or die-offs, but a subtle change in the ratios of things. The forests do not vanish, they merely retreat, band by band, from the interiors of the continents toward the wetter margins, and even there they grow more slowly. Trees that once ran to 100 feet manage 70, then 50. The rings inside their trunks grow closer together year by year, not because the summers are shorter, but because a leaf spending an entire summer breathing an atmosphere with too little carbon dioxide simply cannot manufacture the sugars a large body requires. The wheat and the rice and the soybeans, which are all C3 plants, no longer grow in the yields their old growers relied upon, though of course by then there are no growers and no yields, and no one to count what has been lost. There is only the slow, quiet reduction in green, and the slow, quiet exposure of ground that had been shaded for 400 million years. When the concentration finally crosses the C3 compensation point, the effect is not a bang but a threshold. Below that line, an untended C3 plant in the natural atmosphere cannot produce enough sugar in daylight to pay back what it burns at night. It runs a deficit and then another, and after some number of seasons its reserves are gone and it does not put out new leaves in the spring. The trees do not fall, they simply do not renew themselves. The stands go grey standing up, and the wind and the rain, still following the old patterns, take them apart in their own time. What replaces them where anything replaces them? is not another forest. It is a lower, sparser vegetation, mostly the grasses and the succulents that use the newer chemistry, the ones that learn to concentrate their carbon dioxide. Those latecomers hold on. The C4 pathway is one of evolution's most interesting improvisations, a small anatomical trick worked out independently more than 60 times in unrelated lineages, in which the plant's cells wall off a private inner chamber and use a preliminary enzyme to pump carbon dioxide into it, so that Rubisco, the old and clumsy fixer, finds itself in the middle of an artificially enriched atmosphere and can work at speed even when the outside air is thin. C4 plants are the corn and the sugar cane, the sorghum and the millet, the great tropical grasses that carpet the savannas. They amount to only a small share of the world's vegetation by species. The rough tally puts them at about 3%, against 95 for the C3 majority, and a further 2 for the succulent cam plants that do a similar trick on a different schedule. But their share of the world's productivity in warm, dry, low carbon dioxide places has always been outsized, and in the world of the falling greenhouse it becomes almost total. The savannas expand into the ranges the forests have vacated. The grasses take the interiors. For a long stretch of time, measured perhaps in hundreds of millions of years, the surface of the planet is still green, still productive, still humming with a kind of life that any traveller from our epoch would recognise, even as its inventory has been quietly cut to a small fraction of what it once was. And then the concentration falls further, and the C4 plants too begin to feel the pinch. Their compensation point is far lower. The estimates place it near 50 parts per million, and some accountings push it lower still, but it exists, and the slow drawdown does not stop. At some point measured against the great luminosity curve of the sun, the atmosphere passes below the level at which even the cleverest terrestrial photosynthesis can pay its bills, and that is the end of macroscopic land plants. It arrives, in the modelled schedules, at somewhere near 5 1/3 billion years after Earth's formation for the C3 pathway, and near 5 9/10 billion for the C4. Dates worth naming plainly, because they are the dates on which the green world truly closes, and because they set the boundary between an Earth that still holds forests in some form and an Earth that does not. Beneath and beside this long thinning of the plants, the animals go quietly through their own version of the same story. Herbivores need vegetation, and when the vegetation is thinner and less nutritious, the herbivores must range farther and grow smaller and reproduce less. Large-bodied animals, which need great tonnages of green to fuel their metabolisms, are the first to falter. The great grazing herds shrink and then dwindle. The browsers of the woodlands lose their woodlands. Insect populations, which are the underpinning of nearly every terrestrial food web, follow the plants they specialise on into decline. Pollinators lose the flowers, or the flowers lose the pollinators, and either failure ends the partnership. Carnivores, which sit atop food chains built on all of this, lose their prey base and thin out. It is not a spectacle. It is a subtraction, running for a very long time, and there is nothing in the physics that resembles a pause. The oceans watch this happen, if watching is the word, and for a time they are largely unaffected. The sea is a different chemistry, with its own reservoir of dissolved carbon dioxide, its own pH, its own currents mixing the deep with the shallow. The great work of oceanic photosynthesis is done not by land plants at all, but by phytoplankton, the microscopic drifting cells that fill the sunlit surface layer of every sea, and account for the majority of the planet's primary production. The base of every marine food web, the source of a large share of the atmospheric oxygen, the invisible pastures on which every fish and whale and seabird ultimately depends. Phytoplankton work fast. Where a tree, on average, turns over its living substance across something like 19 years, a phytoplankton bloom turns over in a matter of days, 2, 4, 6 at most. A metabolism running more than 1,000 times faster than the metabolism of a forest. They are old too. Their central enzyme is the same Rubisco. inherited from an ancient common ancestor that arose when the atmosphere was rich in carbon dioxide and poor in oxygen, and it has been carrying the same tension in its chemistry ever since, tuned for an air that no longer exists. That deep antiquity matters, because it means the phytoplankton are, in some sense, more robust to a return to old conditions than the land plants. As the atmosphere's carbon dioxide falls, the ocean's dissolved inventory of it falls too, but the ocean holds a much larger stock and it releases it slowly, and the plankton continue their work for a long while yet. If the story were only about carbon dioxide, they might outlast the forests by an enormous margin. But the story is not only about carbon dioxide. The sun goes on brightening, the surface warms, and warm water is a different environment from cool water in ways that touch the plankton directly. Warm water holds less dissolved gas. It stratifies more strongly, so that the sunlit surface layer, where photosynthesis happens, becomes cut off from the nutrient-rich waters below. The upwelling zones that today feed the great fisheries begin to falter, one by one, as the temperature gradients across the ocean flatten and the winds that drive the upwelling shift and weaken. And the biochemistry of the plankton themselves has its limits. Their photosynthesis has an upper temperature ceiling, past which it slows and then fails, and the ceiling is not especially high. Estimates suggest that a warming of the world's oceans by around 6 degrees would be sufficient to halt oxygen production by phytoplankton across large portions of the sea, by pushing photosynthesis past the point its enzymes will tolerate. 6 degrees, on a planet whose brightening sun is projected eventually to lift surface temperatures by tens of degrees, is not a large budget. And so, in the same long era in which the land is losing its forests to the falling greenhouse, the oceans are beginning to lose their plankton to the rising temperature. The two collapses are not identical in their causes. One is starvation of a gas, the other is failure of an enzyme in heat, but they are the same in their consequence. The primary productivity of the planet begins to fall, and when primary productivity falls, oxygen falls with it, because the free oxygen in Earth's atmosphere is not a static reservoir, but a maintained one, held up minute by the labour of photosynthesizing organisms against the slow oxidative demand of every rock and every breathing cell and every candle flame that has ever burned. Take the photosynthesis away, and the oxygen begins to slip. It slips slowly at first, because the reservoir is enormous, but the direction is unambiguous. The atmosphere Earth has held for the last several 100 million years, the roughly 1 part in 5 of free oxygen, that made possible the large, active, warm-bodied lives that dominate the modern world, is a young atmosphere, in the planetary sense, and a maintained one. It is not built into the rocks, it sits in the sky because things in the sea and on the land continually put it there. As those things fail, it drains. The projections that trace this drainage arrive at a memorable and somewhat haunting conclusion. The oxygen-rich atmosphere our world has known may last only about another 1 billion years, and the atmosphere that follows it will bear a strong family resemblance to the atmosphere that came before it. Low in oxygen, rich in methane, hazed perhaps with organic particles, closer in character to the Archean sky, under which the first cells learn their trade than to the sky above any modern forest. The animals that need oxygen do not have 1 billion years to find another arrangement. The large body ones need concentrations near what they were built for, and they falter as those concentrations slip. Insects, which respire through tracheae that depend on high partial pressures of oxygen to function properly at any body size larger than the smallest, dwindle as the pressure drops. Fish thin out in warming, deoxygenating seas. The complex multicellular, oxygen-demanding lives that have crowded the last 500 million years of Earth's history run out of the substance they were built around, and they follow the plants and the plankton in the long procession downward. This is what the collapse actually looks like when it is stretched out and given its due dimensions. It is not a single ending, it is a series of endings, in a sequence set by the different tolerances of different chemistries. The forests go before the grasslands, and the grasslands go before the plankton, and the plankton go before the last small multicellular animals in the last cool corners of the sea. Each casualty pulls the next one down after it, and none of the losses reverses. It is an extinction era, not an extinction event, and it does not resemble the great sudden dyings of the past, the end Permian, the end Cretaceous, in which a violent stroke opened new evolutionary space almost as quickly as it closed the old. There is no new space opening here. There is only the slow, monotonic tightening of the physical envelope in which any life at all can be done. There is one more thing worth understanding about this era, and it is what makes the picture bearable rather than merely bleak. The complexity goes, but the life does not, at least not all of it. Long after the last forest has fallen and the last plankton bloom has faded, there is still a planet's worth of microorganisms whose lineage predates the forests by billions of years, and whose requirements are far simpler than those of anything larger. They live in places that the surface catastrophes cannot easily reach, and they will hold on in those places for a very long time. For how long exactly no one can say with confidence, but almost certainly for longer than any of the visible life above them. Turn the story for a moment, so that the light falls on those places and on what actually lives in them. There is a spring in the northern basin of the Yellowstone caldera, in the interior of the continent that is now North America, called Octopus Spring. It is a modest pool by the standards of that landscape, its waters clear and blue, its temperature not far below the boiling point of water at that altitude. In the middle years of the 20th century, a microbiologist named Thomas Brock came to it and noticed, along its edges, what he later described as pink gelatinous masses of material, obviously biological at surprisingly high temperatures. From those masses he isolated a bacterium he called Thermus aquaticus, which lives comfortably in water hot enough to scald a hand, and whose enzymes have since been put to work by biologists everywhere in the small chemical reaction that copies strands of DNA. Yellowstone as a whole, in the accountings that followed, turned out to hold more than 1,700 distinct organisms across more than 36 phyla of archaea and bacteria, thriving in waters ranging from around 90 degrees Fahrenheit up close to 200, in springs whose chemistries range from strongly acidic to strongly alkaline, and whose colours come from mats of living cells that make their livings from sulphur or iron or hydrogen or heat. Places like Octopus Spring are laboratories for the far future in a modest way. They contain communities that require no oxygen, or very little of it, and no photosynthesis, or very little of it, and no complex food web at all. They persist on the chemistry of hot water in contact with rock, and they persist because that chemistry is enough. Long after the forests are gone and the plankton are gone and the atmosphere itself has thinned back towards something the Archean would have recognised, the thermal springs, or their analogues, could still hold populations of this kind. Their occupants would be strange to us, but they would not be new. They would be very old. Beneath the great ice sheet of Antarctica, at the other end of the modern world lies another kind of refuge. There are more than 400 subglacial lakes tucked between the ice and the bedrock of that continent, kept liquid by geothermal heat rising from below and by the immense pressure of the ice above. The largest of them, Lake Vostok, was reached by a Russian drill in the late 1990s at a depth of 3,623 meters and yielded pressurized water, ancient trapped gases, and hints of extremophil microbial life. A shallower lake called Willans was sampled in 2013 through 800 meters of overlying ice, and its 2-meter water column, though slim, turned out to be oxygenated and to hold carbon and nitrogen and phosphorus in concentrations more than sufficient to support microbial growth. Nearly 4,000 distinct kinds of microbes were counted there, chemoautotrophs by trade, drawing their energy from dissolved minerals, nitrites and iron and sulfur compounds, rather than from sunlight, which never reaches them and which they do not need. Later, from a neighbouring subglacial pool called Mercer. researchers pulled more than 1,300 single-cell genomes out of the water and the sediments, and found that most of them belonged to organisms new to science, evolutionarily isolated from the surface and marine biospheres by however many thousands or millions of years they had spent sealed beneath the ice. Farther down still, at the bottoms of the modern oceans, along the volcanic ridges where the seafloor is being born, hot mineral-laden fluids rise from cracks in the crust and support entire ecosystems that do their photosynthesis, in effect, without a sun. The primary producers there are chemosynthetic bacteria, which build organic matter not from sunlight but from the hydrogen sulfide and methane that rise with the vent fluids. Around them cluster the tube worms and clams and shrimp and anemones that make their livings by hosting those bacteria as symbionts within their own tissues. In one recently studied vent field in the Gulf of California, at a depth near 3,700 meters, a sea anemone was found to house a previously unknown chemosynthetic partnership of just this kind. The vent ecosystems are not merely a curiosity, they are a proof of concept, a demonstration that life can build its whole economy on the chemistry of the planet's interior without any reference to the star overhead. And there is one more habitat, larger by biomass than any of the others, which most surface dwellers never think about at all. It is simply the rock beneath our feet, the deep subsurface biosphere, the population of microbes that lives inside the pores and fissures of the continental crust, is, by the most careful recent accountings, home to somewhere between 12 and 20% of all the microbial biomass on Earth, most of it in the continents rather than the sea floor. Cells have been recovered from wells and boreholes at depths of 5 kilometers or more. The mean geothermal gradient in the continental crust is about 30 degrees for every kilometer of descent, which sets, for a modern Earth, a rough lower limit of around 3.5 kilometers, before temperatures reach the upper tolerance for cellular life at about 122 degrees. Within that broad envelope, an enormous and largely unexplored population of organisms lives on the slow chemistry of water reacting with rock. Anaerobic methane oxidation, ferric ion reduction, sulfate reduction, hydrogen production from radiolysis of water by natural radioactive decay, reproducing on timescales of centuries or longer, drawing so little from their environment that a spoonful of subsurface fluid may hold cells that have not divided since long before any human civilization arose. Each of these refugees, the hot spring, the subglacial lake, the vent field, the deep aquifer, offers a picture of what remains when the surface has been foreclosed. Each is powered by something other than sunlight. Each has an inventory of life that predates, by billions of years, the forests and the animals whose loss the earlier part of this story has been tracing. And each carries, as its part of the bargain, its own dependencies, on liquid water, on a particular chemistry, on an energy source that the brightening sun does not immediately touch. It is those dependencies that decide how long each refuge lasts, and in what order they close. And of all those dependencies, the deepest and the most quietly essential is water. Not the ocean as a place exactly, but water as a substance. The thin film of it that coats every grain of subsurface rock, the brine that circulates through the vent systems, the liquid pooled beneath the ice, the meltwater that seeps into the pores of the crust. If the surface ocean goes, most of that inheritance goes with it. And it goes not in a single dramatic event, but in a slow, uneven, essentially irreversible drawing down of the world's water inventory, a process that begins so quietly that on any human scale it looks like nothing at all. Consider what an ocean actually does over the course of a year. Somewhere near 114 centimeters of water, a column of it, close to 4 feet deep, averaged across the whole surface of the sea, leaves the ocean each year as vapour, drawn up into the air by sunlight and returned to it by wind and by the difference in vapour pressure between warm water and cooler sky. More than 9/10 of that vapour falls straight back into the ocean as rain. and a smaller fraction moves inland to become the rivers and the aquifers and the snowpacks and the lakes. On average, a single water molecule spends about 9 days in the atmosphere before returning to the surface, which is to say the whole ocean turns itself over into the sky and back again on a rhythm so brisk that, from the perspective of the geologic record, it barely counts as a delay at all. This is the hydrological cycle, and it is perhaps the most familiar of all planetary machineries, the one everyone learns at school in the form of a diagram with little arrows. What the diagram does not show is how sensitive that machinery is to the temperature of the sea, and how the balance shifts as the star above it grows imperceptibly brighter, year after year and eon after eon. A warmer ocean evaporates more water into a warmer atmosphere. A warmer atmosphere can hold more water vapour before that vapour condenses back into rain, and water vapour is itself a greenhouse gas, transparent to the visible light streaming in from the sun and opaque to the long infrared radiation trying to leave, so that more of it in the air means a warmer surface still, which means more evaporation still, and so on around the loop. For most of Earth's history, this feedback has been checked by the presence of clouds, by the cold trap at the top of the troposphere where rising vapour meets air so cold that it condenses out and falls back down as rain long before it can climb any higher, and by the carbonate silicate thermostat that has drawn down carbon dioxide as the sun has brightened. The cold trap in particular has done a beautiful and quiet piece of work for 4.5 billion years, keeping the stratosphere, the layer above the weather, profoundly dry, so that water vapour has been effectively confined to the lower atmosphere where it can be rained back into the sea. The moist greenhouse is the name for what happens when that cold trap begins to fail. It is a state, rather than an event. It comes on over tens or hundreds of millions of years, not in a single summer. In a moist greenhouse, the ocean is still there and life of many kinds may still persist within it, but the stratosphere is no longer dry. Water vapour, in amounts that today would seem impossible, leaks upward past a weakened cold trap into the thin, high air, where the ultraviolet light from the sun, the same wavelengths that ozone filters out down here at the surface, strikes the water molecules and breaks them apart. The chemistry is patient and inexorable. Each broken molecule yields, in effect, a hydroxyl fragment and a free atom of hydrogen. The hydrogen, being the lightest thing in the universe, is not gravitationally bound to the Earth in any strong sense. At the top of the atmosphere, it can wander into space, dragged out by the solar wind, borne away by a small handful of escape mechanisms that operate constantly and quietly across the whole upper envelope of the planet. The oxygen, heavier, stays behind or is consumed by reactions with the crust. Water, once lifted into the stratosphere and cracked open by ultraviolet light, does not, in any practical sense, come back. The rate at which this is happening today is small. The best current estimates put the hydrogen escape flux at somewhere near 2.7 million atoms per square centimetre per second, averaged over the whole of the Earth. That is a number so vast in its counting units, and so small in its consequences, that if that rate had held constant across the entire 4.5 billion years of Earth's history, the total water lost would amount to about 2 parts in 1,000 of the modern ocean. The escape has been faster in the past. During phases of a wetter or hotter upper atmosphere, it may have run orders of magnitude higher, and best estimates suggest the planet has, across all the eons combined, lost roughly 1/4 of the ocean it began with. Even so, the ocean of today remains a bath of extraordinary depth. It is not going to disappear tomorrow, or in 100,000 tomorrows. But the machinery is one-directional. It has been leaking water into space for 4.5 billion years, and it will keep leaking, and as the sun's steady brightening warms the ocean and lifts the water table of the atmosphere, the leak will accelerate. 3-dimensional climate models, the sort that solve the atmospheric equations in full, layer by layer, cell by cell, rather than approximating the whole atmosphere as a single average column, have been able for only about a decade to hazard reliable estimates of where and when the cold trap begins to fail in earnest. the most influential of these published from a laboratory in Paris in the closing weeks of the year 2013, put the tipping point at a mean solar flux of about 375 watts per square metre, reaching the top of the atmosphere, up from the present-day value of 341. A change of roughly 10%, in other words. The same 10% by which the sun brightens across 1 billion years. The corresponding surface temperature at the threshold is on the order of 70 degrees on the everyday scale, or somewhere near 340 Kelvin in the physicists' units. That is warmer than any hot desert on the Earth of today, but it is not warmer than the interior of a well-run kitchen oven, and it is only about 15 degrees hotter than the warmest surface temperatures inferred for the Archean Ocean. Between that threshold and the state we call a runaway greenhouse, there is another interval of long, slow suffering. In the moist greenhouse, the ocean still exists. It is being drawn upward, piece by piece, molecule by molecule, into a stratosphere it never used to reach, and the hydrogen fraction of every stolen molecule is being carried away into interplanetary space, and the oxygen left behind is oxidizing the crust and the atmosphere in ways that begin to change the very colour of the sky. The circulation of the ocean itself changes as it warms. Deep convection weakens where the surface waters stop cooling enough to sink. The overturning that carries oxygen from the sunlit layers to the abyss slows down and in patches ceases. Whole basins become sluggish and stratified, warm on top and stagnant beneath. Fresh water evaporates faster from smaller seas than from larger ones, so the shallow inland arms of the ocean go first, the modern equivalents of the Baltic, the Mediterranean, the Persian Gulf, leaving pale rings of salt behind them where the water used to reach. The great ocean basins themselves, the deep ones, resist longer, but even they are subject to the accounting. The volume of the sea is being drawn on from above at a rate that increases each 100 million years, and the volume returned from below by volcanic outgassing does not keep pace. Slowly the coastlines withdraw. Continental shelves that had been drowned for hundreds of millions of years reappear as broad salt plains, then as new lands, then as high dry country from which the sea has permanently retreated. What had been the edge of the ocean is, in time, half a continent away from the water. A runaway greenhouse is what waits at the far end of this long descent. In the runaway state, the atmosphere itself becomes the reservoir. So much water is held aloft as vapour, and vapour is so effective at trapping heat that no plausible arrangement of clouds can any longer let the planet radiate away as much energy as it receives. The surface passes some threshold temperature, depending on the details, between roughly 350 and 450 Kelvin, beyond which the ocean simply cannot be maintained as a liquid at all. Any remaining sea boils off wholesale into a dense steam atmosphere thousands of times the mass of today's air. The ultraviolet stripping then works on that steam atmosphere over what may be tens of millions of years, until the hydrogen is gone. What is left, once the process finishes, is a bone-dry planet with a scorched crust and a heavy atmosphere of whatever gases could not escape. Mostly carbon dioxide, mostly nitrogen, mostly oxygen chemistries locked away in the rocks, and no ocean at all. For the unsettling neighbouring case, one has only to look at Venus. Venus is nearly Earth's twin in mass and in bulk composition, formed from the same swirling disk of dust and ice, delivered, presumably, its own share of water in its first 100 million years. And Venus is dry. The bulk atmosphere of Venus is so extraordinarily enriched in deuterium, the heavier stable isotope of hydrogen, over ordinary hydrogen that the ratio there is about 120 times what it is on Earth, which is precisely the fingerprint one would expect if a whole ocean's worth of water had been split apart in the upper atmosphere, and the lighter of the two hydrogens had been preferentially lost to space. The current best reconstructions suggest that early Venus lost the equivalent of at least a 3-kilometre deep global ocean by hydrodynamic escape in an early hot phase during which sunlight tore water molecules apart faster than the interior of the planet could replace them. Direct measurements from the European Venus Express mission, in orbit through the second half of the 2010s, confirm that even today hydrogen is being lost from Venus at roughly twice the rate that oxygen is, which is the atomic signature of water being the source of the outflow. Venus, in other words, is not just a planet that happened to end up dry. It is a planet whose water was actively boiled into space, molecule by molecule, in a runaway greenhouse whose consequences we can still measure now, more than 4 billion years later. Venus should not be taken as a simple prediction for Earth. It sits closer to the Sun, receives about twice the insolation, spun more slowly and cooled its interior differently, and may never have had a stable ocean at all. What Venus offers is a boundary, a demonstration that on a world of roughly our size and roughly our composition, running away is a stable end state that the physics of climate is entirely capable of producing. It offers, too, a demonstration of irreversibility. On a world that has lost its hydrogen, the water is not coming back. There is no source in the interior, no comet delivery in modern epochs of anything like the right magnitude, no mechanism that reverses a fractionation once the light isotope has been carried out beyond the reach of the planet's gravity. Water lost from a world is lost from that world for good. Earth is not certainly bound for a full runaway. It may instead settle for a long transitional stretch into a moist greenhouse, hot, humid, oxygen-heavy in the upper air, still with water at the surface, but with the water inventory drawing steadily down. It may pass through that state into something drier and hotter over hundreds of millions of years. It may, if the details of cloud cover and continental arrangement go one way rather than another, hold on to some coastal seas for longer than the simplest models suggest. What none of these routes offer is a way out. The sun keeps brightening, the thermostat keeps tilting, the hydrogen keeps escaping. The ocean, at the end of any of these paths, is smaller than it was, which brings us to the honest question of how confident anyone can be about the timing of any of this. The models, as we have said, are complicated. The three-dimensional climate models that can capture the moist greenhouse transition at all are only a decade or so old, and they disagree with one another in ways that reflect genuine unfamiliar physics rather than mere computational imprecision. The largest single source of that disagreement at present is clouds. Clouds cool the planet by reflecting sunlight and warm it by trapping infrared, and the balance between those two effects depends on cloud height, cloud thickness, the size of the water droplets and ice crystals within, the altitudes at which they form, the way they move as the ocean warms. At the moist greenhouse threshold, the sensitivity of the surface temperature to any change in the energy budget peaks at values several times higher than it is under present conditions, which means small errors in the cloud representation can shift the estimated tipping point by hundreds of millions of years in either direction. The first estimates, made with one-dimensional column models in the last decades of the 20th century, suggested that Earth might tip into a moist greenhouse when the sun had brightened by only about 6%. The full three-dimensional models, with cloud feedback and atmospheric circulation included, have generally pushed the threshold outward to something closer to a 10% brightening, which is, in the end, why the deadline is usually written as roughly 1 billion years rather than 500 million. But the range around that figure remains genuinely wide, with credible estimates spanning from 600 or 700 million years to almost 2 billion. Beyond the clouds, there is the volcanism, which sets the input side of the carbon budget and is itself very poorly constrained on long time scales. Volcanic degassing over the next billion years depends on mantle convection, on the pace at which the continents rearrange themselves and open new ocean basins, on the availability of subducted carbon to be re-emitted at arc volcanoes and mid-ocean ridges. Modern estimates of the contribution of volcanic uncertainty to future temperature projections, even over just the next few decades, can reach nearly half of the total spread of the model ensemble. Extend that uncertainty across 1 billion years and one has no choice but to write the answer in wide bands. Then there are the Milankovitch cycles, the roughly 100,000-year eccentricity, the roughly 41,000-year obliquity, the 20,000-year precession, all of which have marked Earth's climate at the scale of ice ages and interglacials, and will continue to modulate the surface temperature by a few degrees around whatever slower trend the sun imposes. In the greenhouse endgame, these cycles do not save the planet. The trend is one way, but they can shift the exact millennium in which some critical threshold is crossed, adding another layer of ripple to the long descending line. There is also the researcher named Graham at Chicago, whom we have met before in this story, whose recent modelling has argued that if the carbonate silicate thermostat is more weakly sensitive to temperature and more strongly sensitive to carbon dioxide concentration than earlier work had assumed, then the biosphere's window might extend not to 1 billion years, but to something closer to 1.5 or 1 8/10 billion. This is not a rescue. It is a redistribution of a few 100 million years across a very long ledger. It illustrates precisely the shape of the uncertainty. Estimates range from about 500 million to nearly 2 billion years for the end of complex surface life, and the end of the ocean falls somewhere on the far side of that range, but no credible scenario, none proposed by anyone doing this work seriously, restores permanent surface habitability under a sun that keeps brightening. The debate is about the route. The destination is set by the physics of the star. That is the strange consolation, or the strange sharpness of the whole calculation. The deadline is fuzzy in its exact date, and it is razor-sharp in its inevitability. There is no version of the future in which the ocean simply persists forever. There is only how long, and by what path, and with what accompaniment of clouds and continents and volcanoes. Beyond a certain critical brightening, the greenhouse feedback is destabilizing, and the destabilization has an endpoint that is independent of every model parameterization, because it is written into the way that water and light and gravity interact on a warm, rocky world. And so the ocean, which has been the setting for almost the whole of Earth's story, the tide pool cradle in the Archean, the vast oxygenating engine of the Proterozoic, the theatre for the Cambrian radiations, the home of the fish and the corals and the plankton whose photosynthesis even now produces more of the world's oxygen than all the forests combined, becomes, in the long-eyed view of the astronomer looking at the trajectory of the sun, a temporary feature. It is a phase in the biography of a rocky planet. It is the middle chapter, not the whole book. The blue on the globe is only the colour of one long era. Beneath a slightly brighter sun, and above a slightly weakened thermostat, and given enough of the sort of quiet millennium in which nothing much seems to happen, the blue thins to green-grey shallows, then to salt flats interrupted by narrow seas, then to salt flats alone, and each departure of water is, in the ledger that matters, permanent. What has climbed out of the atmosphere and been broken apart by ultraviolet and lost as hydrogen to the solar wind does not come home. There is in all of this a species that knows about it. Nothing else on Earth does. The cyanobacteria that first learned to split water with sunlight, nearly 3 billion years ago now, in the shallows of a warmer sea beneath a dimmer sun, did not know they were beginning a chapter. The forests that spread across the continents in the last 400 million years did not know they would one day be starved of carbon dioxide by a chemistry set in motion long before they existed. The trilobites, the ammonites, the great herds of Pleistocene mammals, none of them, so far as anyone can tell, ever looked up at the sun and computed how long the arrangement was going to last. That computation is a very recent thing. It belongs to one lineage on one planet, and it belongs to a stretch of that lineage's history so brief that if the age of the Earth were compressed into a single day, the whole span in which anyone has known how a star works would fit inside the last fraction of a second before midnight. And yet, in that fraction of a second, a species has looked up and looked outward and looked forward and asked how long and been given an answer. It is a strange kind of inheritance. It is knowledge no ancestor ever carried. And it changes, in a way still unresolved, what the story of a life on this planet actually is, because for the first time, one branch of that story can see the shape of the whole. Return with me, one more time, to the Earth that this whole long calculation has been describing. Not the Earth of tonight, with its ice caps and its rainforests and its scattered lights along the coasts, but the Earth of 1 billion years from now, under a sun that has grown by then roughly a tenth brighter than the one you saw this evening. It is worth trying just once to stand on that surface in the mind's eye, because the strangeness of it is not in what is missing, but in what remains. The sky is still blue at midday, or something close to blue, thinned toward white where the water vapour has thickened it. The sun still rises in the east and still sets in the west, and it still looks to any eye that might be there to see it, like the same yellow star that has kept faith with this planet for 4.5 billion years. It is not visibly larger. It is not visibly hotter. A person standing on a hillside on that far earth, looking up, would see the same disk in the same colour, casting the same soft round shadows that fell across the grasses of the Serengeti and the wheat fields of the Ukrainian plain. That is the first thing to sit with. The end of the world that could hold anything alive does not arrive with a dimming or a swelling or any visible change in the star at all. It arrives beneath a sun that still looks the way it looks tonight. The ground below that sun is another matter. The carbon dioxide has thinned. It has thinned slowly over hundreds of millions of years, drawn down by the same patient weathering reactions that have kept the thermostat honest through every warm interval of the last 3 billion years. Rainwater carrying atmospheric carbon into the silicate rocks, the silicates breaking down, the calcium and the bicarbonate flowing to the sea, the carbon locked away in the slow burial of carbonate on the ocean floors. When the sun was fainter, the thermostat added carbon dioxide back through volcanoes as fast as the weathering pulled it out, and the balance held. Under a brighter sun, the weathering runs faster because the surface is warmer, and the rains are heavier, and the volcanoes cannot keep pace, and the carbon dioxide is drawn down and down and down, past the levels at which the forests of our own time could survive, past the level at which the C3 plants, the oaks and the pines and the grasses of the northern meadows, the wheat and the rice and the soy, roughly 95% of all the plant species alive today, can still gather enough carbon to grow, and then, later, past the level at which even the more frugal C4 plants, the corn and the sugar cane and the savanna grasses, that make up only a few percent of the species, can hold on. The cam plants, the succulents that open their pores at night to steal what carbon they can from the cool air, hold out a little longer still, and then they too fail. On that far earth the continents are not green. They are the colour of stone and of dust and of the pale salts that gather where standing water once was. And yet the water is not all gone, not yet. This is the middle of the passage, not its end. There are still seas, though they are smaller than the ones we know, and their edges have crept inward from the shorelines of our maps, and the great continental shelves that once held reefs and cities lie exposed as pale plains cracked with old river valleys that carry only occasional flash floods. The air above those seas is heavier with vapour than any air a human being ever breathed. The days are hot in a way we would not survive without shelter, the nights only slightly cooler, because the water in the atmosphere holds the heat like a blanket and will not let it go. And in this atmosphere, which has grown moister and moister as the warmer ocean has evaporated more vigorously, the cold trap at the base of the stratosphere is losing its grip. Water vapour is leaking upward, in slow, small quantities, into altitudes where ultraviolet light can find it and break it apart. The hydrogen from those broken molecules is climbing away, atom by atom, into space. The oxygen it leaves behind is rusting the rocks. This is the beginning of the last, longest phase of the ocean's departure, the phase in which the ocean does not so much boil as slowly bleed into the sky. The great oxygen atmosphere we breathe tonight is thinning in that far time. When photosynthesis fails on the scale it has run at for the last 2.5 billion years, the oxygen has no source that can replenish it, and it is consumed steadily by the ordinary chemistry of the rocks and the residual life, and it falls. Within some hundreds of millions of years of the failure of the last great forests, the atmosphere reverts to something the earliest Archaean would have recognized: low in oxygen, higher in methane released by anaerobic microbes in the sediments, dense with water vapour, hazed and hot. The ozone layer, which the oxygen once built, thins with it, and the ultraviolet reaches the ground unimpeded, sterilizing every surface it touches. Life, by this point, is not on the surface. It is in the films of water between grains of soil, in the deep aquifers, in the hot brines that pool a kilometre down and more, in the geothermal springs where chemistry alone can feed a microbial mat that does not care whether the sun is shining. There are refugees. There are always refugees for a while. The subglacial lakes are gone, of course. The ice is gone. But the deep continental biosphere is still there, sustained by the heat of the Earth's own interior, feeding on the slow radiolysis of water by uranium and thorium and potassium in the rocks, indifferent to the star above. The last complex ecosystems, the ones we would recognize as ecosystems at all, the last pond with its algae and its worms and its small crustaceans, the last salt marsh with its cyanobacterial mats, have long since faded by then. Somewhere in the sequence, without any single moment that a record would mark as the moment, the last flower opens and is not followed by another. Somewhere the last vertebrate takes a breath and does not take the next one. Somewhere the last coral polyp closes for the last time upon a warming, acidifying, brightening sea. There is no meteor for these endings. There is no volcano. There is only, in the ledger the physics keeps, one photon too many, over 1 century too many, pressing down on a planet whose thermostat has run out of room to move. And above it all, in the sky, the same yellow sun that shone on the first cyanobacterium in the shallows of the Archean Sea shines on the last drying pan of salt where anything that could once be called a forest ever grew. This is what it means to say that life on Earth ends not with darkness, but with too much of the very thing that made it possible. The sun is not the villain of the story, it is the protagonist of it. Every leaf that ever unfurled did so because a photon arrived. Every reef that ever built itself in the shallows did so because the light reached down through the water and warmed the coral and fed the algae in its tissues. Every whale song that ever travelled through the deep did so at the end of a food chain whose first link was a plankton splitting water with sunlight. Every city with its lit windows, every field of wheat with its ripe heads bending in the wind, every child running across a summer lawn. All of it is a single long inheritance from a single star, tuned to a single narrow set of conditions in which the star was neither too dim nor too bright, in which the atmosphere was neither too thick nor too thin, in which the water could remain liquid at the surface long enough for the slow chemistry of life to take hold and complicate itself into everything that has ever complicated itself. The gift did not fail. The gift became too much. There is in that framing a kind of tenderness that is easy to miss on the first pass. The star did not turn against the world it enabled. It simply kept doing, more and more, the thing it had always done. And the world it made could hold that gift only up to a certain measure, and no further. And so a person standing on that far hillside, if such a person could stand there, and looking up at that unchanged-looking sun, a person who somehow knew the whole history of what had been lost, who could have listed the coral and the dinosaur and the whale and the human city as things this same star once made possible, would not be looking at an executioner. They would be looking at an elder. They would be looking at the source of everything that had ever been, still shining, still faithful, still giving, only now giving a little more than the small blue and green world beneath it could receive. That is the true shape of this ending. It is the shape of a candle burning down its own room. It is the shape of a hearth grown, over long centuries, into a furnace. The heat that once made the home possible is the heat that at last empties it. There is no cruelty in it. There is only the arithmetic of a star that must, by the nature of its fusion, brighten as its core fills with the ash of its own long labour, and a planet whose habitability was, from the beginning, a negotiation with brightness. When brightness wins, habitability ends. When the gift outgrows the giver's careful measure, the room grows quiet, and the last daylight, which looks exactly like the first daylight, falls across a floor that has no one left to walk on it. It is worth sitting for a long moment with the strangeness of that image, because it is the image the whole calculation resolves into, and it is not the image most people carry when they think about the end of the world. The end of this world is a bright day. It is a bright day on a warm planet beneath a familiar sun, and there is no one there to notice. Turn the story for a moment so that the light falls on the present instead. Because the far end of the story is not where we live. We live at the beginning of the last long chapter, not at its close. The billion years between now and the failure of complex life is not a countdown to catastrophe, in any sense the human nervous system can hold as urgency. A billion years is a length of time so long that language, as it has been spoken by any living person, breaks against it. If the whole 4.5 billion year history of the Earth were compressed into a single calendar year, the last billion of it would occupy the final 2.5 months. Everything from the first stromatolites to this evening would fall within the first 9.5. Human history, all of it, from the earliest pressed clay tablet to the last message sent over the network before you started listening tonight, would occupy the last second before midnight on the 31st of December, and the billion years remaining to the biosphere, in the shape it has taken these last few 100 million, would still be more than 8 weeks of that year to come. Whatever is coming for this world is not coming soon in any register the human body knows. 100 human lifetimes end to end would not reach the outer edge of a single one of those weeks. 1,000 would not. The far ending is real, and it is fixed, and it is also, from where we stand, almost inconceivably distant. That distance matters. It matters because it separates two entirely different responsibilities, and one of them is very old and one of them is very new, and confusing them does damage. The old responsibility is the one written into the star itself. The slow brightening cannot be stopped, and the ocean will thin, and the forests will fail, and the last daylight will one day come, and none of that is anything a species can prevent, however wise, however careful, however loving of the world it happens to be. The new responsibility is the one written into the last few centuries. A species has learned to move carbon out of the rocks and into the air faster than the thermostat can compensate, and to move species around and out of existence faster than the biosphere can heal, and to alter the chemistry of the ocean and the composition of the atmosphere and the surface of the land on timescales measured in decades rather than in eons. The billion-year deadline is not a permission slip for the century-scale one. It is the opposite. It is the reminder that the biosphere's remaining span is so long and so precious and so difficult to have made in the first place, that shortening it by even a fraction of a percent through carelessness in a single generation would be a loss out of all proportion to any gain. The sun's slow work will end this world eventually. Nothing we do to the world in the next 1,000 years will change that ending by more than the width of a hair. But nothing about the sun's slow work absolves any generation of what it does, in its own time, to the systems the sun has made possible. Consider, for a moment, the ocean. Not the ocean of 1 billion years from now, which is a thin salt sea beneath a heavy sky. The ocean of tonight, the one whose plankton, right at this moment in the dark under the Pacific and under the Atlantic and under the Indian and under the southern seas, are still splitting water with the light of the following morning, are still generating more than half the oxygen that will enter the next breath any human being takes. That ocean is a temporary achievement. It has not always been the way it is now, and it will not always be. It is the middle chapter, told in warm currents and cold currents, and the long, slow, overturning circulation that moves heat from the equator to the poles and back. It is a rare balance, and it has held long enough to have grown corals into reefs and reefs into whole architectures of life, and it is holding still, at this hour, in the dark, everywhere the tide is running. It is the same substance that will one day climb into the stratosphere and be broken apart by ultraviolet and lost, but it is not lost yet. It is here. It is here in a way that, seen against the whole trajectory of the star and the planet, is almost impossibly precious, because it is the sort of thing that only exists during the narrow window when the star is neither too dim nor too bright, and that window, for this world, is where we happen to stand. Consider the forests too, not the ghost forests of the far future, but the ones that exist tonight. The boreal spruce forests running from Alaska across Siberia and back around through Scandinavia, the tropical rainforests along the Congo and the Amazon and the great islands of the Western Pacific, the temperate deciduous forests of eastern North America and East Asia and Central Europe, the eucalyptus forests of Australia. All of them are temporary. All of them exist because the carbon dioxide is still, for a little longer, above the level at which their photosynthesis can gather enough to build a leaf. All of them will one day fail as the thermostat pulls the carbon down past the threshold their chemistry requires. But that failure is 1 billion years away. Tonight the leaves are still opening and closing their pores in the dark, still holding the small chemistry of chlorophyll ready for the morning. Tonight the trees are still standing. Consider the atmosphere itself. The blue mixture of nitrogen and oxygen and trace argon, and traces of everything else. The atmosphere whose oxygen was set into place by 2 great oxygenations, one nearly 2.5 billion years ago, and one between 800 and 600 million years ago, and settled at roughly the 1/5 of the air that it is now. That air is a temporary achievement of a biosphere that learned to split water with sunlight and did not stop. It is not a background condition of the planet. It is a construction. It has a beginning and it will have an end, and the end is written into the same brightening that will end everything else. Between the beginning and the end there is a middle, and the middle is where every animal that has ever taken a breath has lived, and it is where you are living now. That is not a small thing. Nothing about knowing the far end of it makes it a smaller thing. There is a paradox at the heart of this whole night's telling, and it is worth naming plainly before we close. It might seem at first that knowing the biosphere has a deadline, that all the coral and all the forest and all the whale song is bound one day, for a bright silent end beneath an unchanged-looking sun, should make the living world feel smaller. It should make it feel provisional. It should make it feel less worth caring about, since caring about it cannot save it in the end. But that is not what the knowledge does when it is held long enough to settle. What the knowledge does is the opposite. It makes the living world feel more consequential, not less. It makes the fact that any of this exists at all, that there is a planet on which water is liquid and green, things grow and animals move through them, and one strange lineage among those animals has learned to compute the whole trajectory, feel less like an ordinary state of affairs and more like a rare accident of light and gravity and chemistry and time. The forests are not less precious for being finite. They are more precious. The ocean is not less astonishing for being a middle chapter. It is more astonishing because middle chapters on rocky planets around brightening stars are what the whole story turns on, and there is only ever one of them, and this is the one we happen to be inside. Losing the ocean, in the end, is not the same as losing what the ocean has been. Every reef that has ever grown, every plankton that has ever bloomed, every wave that has ever broken on a beach at any hour of any night for the last 4 billion years is a thing that happened. It is not undone by its ending. That is the strange, quiet comfort of a universe that runs forward. What has been, and the far arithmetic of a brightening star cannot reach backward and unmake it. The last daylight, when it comes, will not erase the first. It will only be the closing of a very long day whose morning began in the Archean shallows and whose noon we are standing in. The sun is still climbing tonight through its long middle age. It is doing what it has done for 4.5 billion years, and what it will do for another 5 or so before its own story ends in a very different way. It is fusing hydrogen in a core 15 million degrees hot, and it is losing 4 million tons of mass every second as pure light, and some small fraction of that light is falling right now on the night side of a rocky planet through the medium of a full moon or a starlit sea or the reflected glow of a distant city, and some larger fraction of it in about half a rotation from now, will fall on leaves and on ocean surfaces and on the closed eyes of everyone who slept through this. The gift is still arriving. It has not yet outgrown the room. Everything that lives on this world tonight is living inside a window that opened long before any of us and will close long after. The window's real, and the closing is real, and the light that is coming through it right now is real too. There is nothing to do with that knowledge except to hold it, and to love the world it describes a little more carefully, and to remember, when the sun rises in the morning, that it is the same sun that will one day be too bright for anything to bear, and that its brightness this morning is exactly enough. It is enough for the trees, it is enough for the tides, it is enough for the plankton in the dark water, and the birds that will begin, at the first pale edge of the sky, to sing. Thank you for travelling out to the edge of everything with me tonight. Keep looking up, take good care of one another, and good night.